1 is definitely even. The E is definitely even. If I invert this thing, no change of sign. But this is definitely odd. Invert that, it changes sign. It's a dipole. It's odd. Okay, as opposed to even. All right? Now, this is a sort of a ghost of the angular momentum states that you might expect on an octahedron, the subgroup of a sphere. This is the S wave, this is the P wave, and this is the beginning of the D wave, the angular momentum 2 wave, tensor, you see. But it doesn't have enough dimensions to show the other 3, which will belong to T2. That will make 5 states that correspond to the 5 states of quantum angular momentum. 2, 1, 0, minus 1, and minus 2. That's 5. Okay? We only get to use 2 here. But we can use all those. Okay, so that's another way to look at all of this. And that's, of course, what Beta was doing, because he's very good at that sort of discussion. So that's the end of this, as I like to say, either the first or second most terrible lecture that we have to do. We still have one more to go here. Now, I would like just to add on to this the stuff that's in that article in the International Journal of Molecular Science, where I categorize all of these possible states that you could have with all of the possible parameters. This is a complete invertible sum. If you were to give me all of this possible spectra, not just of the thing we looked at, but all of the things that you can do on an octahedron, I could tell you what your tunneling parameters were, and vice versa. If you're just using the I parameters, remember we showed a matrix with all the I's in it? If you're just using that and you work with the 1, 2, 5, and 6, as opposed to the guys that are on the axis, which are 3 and 4, if you work with these as your local symmetries, then you are diagonal, and you will get something that looks like that. Well, that's what we have. We have twice as much there as we do here, and this is actually showing the signs that this gives directly. But we know that, in fact, these coefficients actually should have a minus sign on them. But if you use the other guy, the I3, 4, to split it, then the T1 comes out, and the other two remain degenerate. So there's a very big difference between these two local symmetry possibilities. Well, the I3, 4 is across the thing that we said was too tiny to matter. So you have to find a channel or something for it in order to make a system that would have that spectrum. And of course, a linear combination of these two would be a linear combination of these. So that would be enough to put the levels anywhere you wanted to. This is the matrix that we were talking about before. Okay, now I'll just point out where these things appear. You can see one right there. A1, T1, and E. Now why is there only that one? Well, if you were to go through a couple of others, you'd find it again here, but here it's broken up. So it's not a terribly good example. There's the A1, T1, E, but here's the A2, T2, E up here corresponding to something that is not divisible by 4, but is still even. And remember, each of these is characterized in case we're talking about angular momentum 30 here. This is the actual spectrum. This is a picture of an energy surface on which these things live, and that's what we've got to develop later on to understand what's really going on here. Because we're talking about angular momentum 30, and these are states. That there's 2 times 30 plus 1 is 61 angular momentum levels all the way through this thing to the very last one at the bottom here. And this is true for every one of these bands. You see, every one of these bands here has a connection to this business that we're talking about. So these are the induced representations of 0 mod 4 to the octahedron from C4 of 1 mod 4, and let's be careful here, 30 is 2 mod 4. It's 28, which is divisible by 4, plus 2, so this is 2 mod 4, and this is 1 less, 1 mod 4, and then this is 0 mod 4. And then this is minus 1 mod 4, and then this is minus 2 mod 4. It's the same as this, and so forth. For each of the levels on these fourfold symmetric fire plug valves, or whatever you want to, I mean, some people say it looks like the Michelin Man, but then where's the head and the arms and the legs? It's too symmetric to be the Michelin Man. Anyway, that's what before we're through with this course, I'll be able to explain how angular momentum cones give us a pretty good approximation to where these things should exist on the rotational surface. And also, this surface itself is something you derive by symmetry projection. So it's a real group theory problem. You have to take the group theory to a new level to do this. So there's the whole spectrum for just one bump. Just one bump, 88th bump, all these things are sitting there. And the A1, T1E is here, 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 starting to come apart here, and then we begin to live in the valleys, which are 3 symmetric, you see. So this is really a different chemical than the stuff on this side. For this molecule, rotating at high angular momentum comes in many different kinds. These are symmetry species for the molecule. That's the name that's given to them. So, you know, this is SF6 classically, but this is the quantum mechanics behind it. Every one of these bumps does that. So it's a real carnival in symmetry analysis of quantum waves.
I can't remember. I think you did mention what type of motion was it that each one of those peaks represents, or is it just
well, it depends on whether you take the viewpoint of the laboratory, in which case there's an angular momentum vector that's constant, an approximate angular momentum vector that's constant. It's a little bit of fuzz to it, but it's, with J equals 30, that's pretty solid. So within about that much, you know where the J is. And then this thing is turning underneath that J in the most bizarre way you can imagine. And the only way I like to imagine it is imagine I'm riding on this thing, okay? So now the J is the thing that's moving, right? But that J, you see, that I started out, say, on a nice state here, begins to get these guys excited. So the J ends up going multiple places. And that's the thing about quantum mechanics, right? You talk about something that's classical, and it's there, and then it's somewhere else, or somewhere else. It's always one place, right? J does not obey that either. Okay? J can be all 6 places at once. That's an A1 state with the same phase. Or it can be with twice the amplitude up here and minus half the amplitude right there. And that's an eigenstate. That will not change. That will actually be quiet. But if you mix 2 of them, then it starts to beat. And if you mix them just right, you can put it all on one of them, and then it starts to die, but it's going to be pi over 2 ahead of the phase of these, gets these guys going, you see, as far as the angular momentum. The angular momentum is the thing that's moving in this frame. And it'll do that whether this is in a quantum ground state of vibration, in which these are just fuzzballs that don't move, or if it's in an excited state, and that's what it will be if you shine a laser to make this spectra, in which you have one quantum of vibrational motion of this thing, and then on top of that, the J is going to be doing its dance amongst these moving guys. And all this is ignoring the nuclear spins, which are also getting into the act, but that's another story for later. So there's a lot going on in sulfur hexafluoride and any other molecule that you can think of as comparable in complexity. So it's a mind stretcher. It's a real mind stretcher.
It's kind of like
Scares a lot of people away.
Sort of off-topic question, I guess, with that, but
Say again.
do people try to incorporate? I know it's really small, but in some way, gravity into that situation.
As far as I know, we're lucky to have even the smallest relativistic effects, that being Compton scattering. This molecule and others like it have been measured by the French spectroscopist who built an incredible spectrometer using an entire factory. It consists of a tube that's more than a couple of meters in diameter, as I remember, and 30 meters long. And the idea is to make a 10 micron electromagnetic wave with virtually no curvature. Several kilometers of curvature, so it's really flat. And back and forth it goes. And as it goes, it will, because you know, at any moment the wavefronts are near each other, and the Doppler shift for them, in other words, what you're looking for are the molecules that are not moving, who see the same frequency for the wave that's going this way as they do for the wave that's going this way. Okay? There are a few molecules that aren't moving. And they register absorption on this. It's called Lambda Spectroscopy. The Lambda was, well, he discovered that there was a dip when the waves crossed. It was due to the fact that you were addressing a population that wasn't moving. So you look at the absorption spectra using that, and you can measure the very finest structures on here. And I'm talking about stuff that's below this diagram, but you can certainly get stuff that's out in here. Kilohertz spectra, no problem. They can measure to within a fraction of a hertz. But when they do that, they see that when the molecule spits out this tiny, weak infrared 10 micron photon, that the whole molecule recoils ever so slightly. But it's enough to observe the Compton shift. So there's an example where a relativistic effect is being observed in the infrared. I mean, it's real. You know, you're talking about several hundred terahertz, and you're measuring that to a precision of 1 hertz. So you get one part in 10 to the 12th is what these guys were able to do, the Bordays. They conned the French government out of millions of dollars to do this, because they promised that when they got done, they would be able to separate uranium hexafluoride. And that's where all of the spectra that I'm showing you on the wall here comes from. When it's the American Los Alamos group that was trying to do what was called MLIS, that's molecular laser isotope separation. The dream was that we would have nuclear power with no expense. And if it wasn't for the waste, that might have come true, but the trouble is there's the waste from nuclear factories. And also there's danger of terrorism. It's so easy to separate the uranium-235 from 235, you're going to have nuclear terrorism. So there's a whole political dynamic that's hiding behind all of this wonderful stuff here, which I had very little to do with. But the understanding of the molecules what Douglas wanted to do. And your original question was, can you feel gravity? Not that I know of yet. In other words, these things the spectrum is taken quickly enough that the molecule would not fall appreciably. And it's horizontal, so you're talking about molecules in a plane like that, and so it conceivably would fall, but the effect of the falling would be second order Doppler, which is not going to be observable at all. Someday.
I actually do have to go because it's across the street.
Look on ResearchGate. There's a lot of nice articles from Bourdais' group. Really
Yeah.
interesting ones. I think
Sure.
I have some of them posted.
Yeah.
They're there.
Yeah, the lab doesn't exist anymore, but it was amazing while it did. Yeah. Okay, we'll catch you tomorrow, I guess. We'll